Good morning. I'm going to start string matching using finite automata. This is in continuous with my previous lecture on string matching. So, what are the content? I'm going to cover introduction to string matching, just like what is string matching and how it is going to play the role in the computer science. And second one is string match introduction to finite automata. Everybody is aware about the finite automata, still I want to introduce. And third is string matching using deterministic finite automata. And fourth one will be string matching using suffix automata. Suffix automata is like a special kind of automata which is only accepting the suffixes of a given pattern. Last is string matching using non-deterministic finite automata. We'll be talking about bit parallelism. So, what is string matching? Actually, given a pattern string P of length, let's say M, and a string S of length, say N. So, generally M is always less than or equal to N. Pattern length is always less than or equal to text length. So, actually string matching is to find all locations in the text where P occurs in the text, like see, consider pattern ABA and this is your text S. So, as we can see that ABA is occurring over here and occurring over here, and there is overlapping occurrence of pattern ABA. So, we can see that ABA is here. We are going to get the starting location of a pattern. Then another ABA is over here and there is overlapping pattern. So, what are the uses of this string matching? We know that this is general regular expression print. This is very important in the Unix regular expression, Unix searching. Second one is very popular in searching. Generally, we are using this string matching in Google search and so many places. And even in our Microsoft Word, we find and replace command. We are using string matching over there. And then another one is java.language.string.content. So, everywhere we are using string matching applications. So, how many types of string matching are there actually? So, we have three types of string matching in the literature. Number one is exact, which we are talking about exact, we call it traditional string matching. Second is approximate string matching. Third one is parameterized string matching. They are generally going to be discussed in the undergraduate text, but this is postgraduate, and parameterized is also for postgraduate student. So, what is exact string matching? In exact string matching, we are finding pattern inside the text without having any error. Like see, if consider A is ABC, so we can see that this is occurring over here, this is occurring over here. So, we can say that pattern occur with shift G, we are taking 0, then 1, then 2, then 3. So, shift is 1 starting from 1, and then another shift is 4 starting from here. Yes. So, and the second category of string matching algorithm is approximate string matching. Generally, we are using this in Google search. So, in this approximate string matching, we are finding pattern inside the text, but certain error can be allowed in the matches, right? So, that error can be calculated using Euclidean distance and edit distance. So many distance measures are there. So, these errors can be in the form of insertion, deletion, and substitution and transposition. For example, like see, insertion is like delta epsilon A. That means we are going to insert A in the text. Second category of operation is deletion, where we can delete A from the text, and replacement, we can replace A by B. And third one is generally we are using it as a transposition. So this is AB can be replaced by BA. This is transposition. So consider the example. For example, if we have survey and another text is surgery, and allowed error is given as 2. So we can see that this is surgery is text and this is survey which is pattern. We can see that this is matching over here, this is matching over here, and this is matching over here. If we can replace G by V and like R by V, we can see that this is matching over here. This section is matched with this section. Only two replacements are there, right? So another like if we can see here survey surgery is there, again we can say one replacement and one deletion. We just delete this, we will get the pattern inside the text. Delete R. Once we delete R, and we can see that this is matching, this is matching, this is replacement, right? So only one deletion and one replacement is still error equal to 2. Error equal to 2 is given in advance. Another operation which is possible, that we can insert this guy over here and insertion R, and we can replace G. So one insertion and one replacement. So that means by allowing error, 2 error, pattern is matching in the text in 3 positions. Okay. So third category which is very popular, we call it parameterized string matching. Actually in this category of matching, we are given 2 kind of alphabet. One is sigma, which we call it fixed alphabet, and other is pi, which we call it parameterized alphabet. So this parameterized alphabets, in this fixed alphabet, symbol from this fixed alphabet cannot be renamed, while symbols from this parameterized alphabet can be renamed, right? Generally this kind of string matching is very popular in clone detection and plagiarism detection. Most of the plagiarism software, they are using this parameterized string matching. So consider this example, like see, suppose we have one section of code in the left hand side where A is 2 and B is 3 and C. This is a C code, and now I am just going to add C is A plus B and print C, right? So suppose any student has renamed the variable, like C, in place of A he is writing X, and in place of B we are writing 3, and in place of C we are writing Z. Z is X plus Y. Same thing, it's just like renaming of the variable. So we can say that this code and this code, they are equivalent. There is no difference, only because of this A was mapped to X and B was mapped to Y, and then C was mapped to Z. That means these two code remain the same. There is no difference between this code and this code because of this. So we can say that parameterized alphabets, they are like sigma A B C can be renamed with X Y Z. So while constant cannot be renamed, right? So this so you see, so we can say that two strings are equivalent if one can be transformed into the other via one-to-one mapping. So this mapping, like see, we transform A to X and B to Y. So this should be consistent within a text. It's not like sometime we are transforming mapping A to Y and sometime we are mapping B to X. So this should be consistent. So in the process of correspondence, some symbol match exactly, whereas some symbol may be renamed, right? So this is very popular and generally we are using in plagiarism detection. So very first method of string matching everybody is aware, like see, is naive approach, like brute force approach, and this algorithm has so many drawbacks because of its time complexity. We'll see that how we can improve the naive based algorithm, naive approach, like see, and given this text and given this pattern, right? So if we see that in this naive approach, we are comparing one by one from the left. A is equal to A, B is equal to B, and then C and D, there is no match. So what we will do, since there is no match, we will shift the pattern by one. If all the shift we are going to consider, again there is no match, again we are going to shift the pattern by one. Again there is no match, so again we are going to shift it by 1. So there is a match, we will stop over here. In order to get the next match, we have to write A, B and D again. We'll continue until we finish the text. So this is very expensive algorithm because it is not intelligent, and this is not working when we have pattern like suffix which is also prefix. This kind of algorithm will not be very efficient, although it will work, but it will not be very efficient because this is not going to use this prefix and is not going to use this information. So this will just take one by one and find out all the valid shift. So its worst case time complexity is very high actually, and it is not very intelligent. So most of the literature, they will not encourage you to use naive string matching algorithm. So what is solution of this kind of problem? That if we want to match A, B, C, A, B, or C, suffix is also prefix, or like C, A, B, C and D and then ABC. This is also matching. So in this kind of situation, we have to find out some alternative to the naive algorithm, which are given by suffix automata and finite automata, bit parallelism, many alternatives, even Knuth, Morris, Pratt, many alternative algorithms are given in the literature. So I'm just going to discuss what is finite automata and how it is going to used in the string matching. As all we know that finite automata is defined by 5 components, right? So if we define finite automata Q, sigma and then delta and Q0 and F. This is finite automata, where Q is finite set of states and sigma is set of input and Q0 is starting state and F is set of all final states. Many final states may be there in a finite automata, and delta is basically a map from Q cross sigma to Q. This is map. Actually, this is category of deterministic finite automata, right? So this delta taking a state and taking input, and then it is going to the other state, right? So this is definition of the DFA, right? So Q set of all states, sigma set of input symbol, delta is a transition function which is defined by this. Q0 is starting state and F is set of all final states, like C. Q0 is the start state and set of accepting state may be more than one. Sigma is the alphabet like C. Q0, if we are applying A, we are going to get Q1, and Q0B, again Q0B, we are going to get Q2. This is transition function, this is doing something, and Q1A actually is going to get only Q1. So all these finite states, these states, they are working as a memory actually. So they will remember the input and they will remember the state of the finite automata. So what is operations? You see, look at here, consider this finite automata. So it is always starting from the start state and it will accept the input when it is reaching to the final state, right? Yeah, if it is not reaching to the final state on a particular input, that means it is not going to accept the input. So yes, so question is that suppose this is your finite automata, of course this is DFA, suppose this is DFA. Okay, so question is that what pattern does this represent? This is representing some pattern, definitely, like see ABA can be accepted, AABA can be accepted, same thing ABB, ABA can be accepted. So it can accept so many pattern. So yes, so consider pattern ABA. So you definitely ABA, look at here, we will start consider this pattern and we have just designed automata for ABA. Now consider this text string, we are starting from Q0, on B we are still at Q0, again on A we are going at Q1, again on B we are reaching to Q1, this new state, let's say Q0, Q1 and Q2 and then Q3. Then again on A we are reaching to the final state, this is Q3, we are reaching to the final state. That means this ABA is over here, pattern is like this is the match. Then again read B, after reading B we are still going to get Q1, then again reading B, it is coming to Q0, then again reading A, it is again restarting, going to Q1, again B, going to Q on a new next state, and then again A, reaching to the final state. That means this is also going. So state doesn't matter, this is Q0, Q1, Q2, Q3. We can give them different name, there is no problem. Then after reading here, again reading B, you are going to get Q1, and again reading A, we are going to get Q1. So this is utilizing, it is not like every time it is starting from the beginning and searching for the pattern. So this is utilizing the suffixes and prefixes also. So when we are talking about finite automata as a string matcher, we are always interested in getting this suffix function, and this is very important to understand what is suffix function and how it can help in designing a finite automata for the given pattern. So the suffix function sigma for a given pattern, actually suppose pattern is given from 1 to m, is this is a map, sigma is a map from sigma star to 0 to m, such that sigma x is the length of longest prefix of p, that is also suffix of x. So consider this pattern P is AB, and if we are interested in finding CCAB with this pattern, so question is that length of longest prefix of P, how many prefixes of P are there? Length of longest prefix of P, that is also suffix of X. So how many suffixes this guy can have? This can have epsilon, B, AB, and then CAB, and then CCAB. So it is very easy to get what is there out of these suffixes. Out of these suffixes, which one is actually pattern P? So look at here, epsilon is always there, B is not matching as a prefix, right? B is not matching as a prefix because its prefix are A and AB. Now AB is matching as prefix of P. So what is its length? Its length is 2. So its sigma of CCAB is 2. Same thing, this will not match, this will not match. Same, consider ABA. What are its suffixes? Its suffixes are epsilon, and then A, and then BA, and then ABA. It has 3 suffixes, right? So which suffix, which one is the longest suffix which is also prefix of P? So if we can see that sigma, then A is prefix of P. Definitely BA is not, ABA is not. So its length is 1. Very simple. So same thing, if you are interested in suffix function of ABB, actually, so what are its suffixes? Epsilon, then B, then BB, and then ABB. Actually, none of them they are prefix of AB. B is not prefix of AB, BB is also not, ABB is also not. So only epsilon is the prefix of this pattern. So its length is 0. So that's why sigma of ABB is 0. So it is very easy to find out suffix function of a corresponding to a particular pattern. You can get given a pattern, so we can get suffix function. How to calculate suffix function for a particular string with respect to the pattern. So building a string matching automata actually, so is like basically it is depending on the concept of the suffix. So consider this pattern ABA, BA, CA. Question is that how to build suffix automata, how to build suffix automata for this pattern. So it's very simple, just like consider suffix finite automata. Consider this, all these states. Actually our finite automata will be having a state number from 0 to m, where m is final state and 0 is starting state. Meanwhile, in the middle something is there. So corresponding to each symbol plus a 0 is starting state and m is only final state. So the transition function is defined as this. This is the main concept in this finite automata, transition function. So if we are interested to get the transition function from a particular state on a particular input, we have to apply this formula delta, like q comma a. If you are interested an input a, and what is value of q and a, basically you need to calculate sigma p q of a. That is the idea of the suffix finite automata. Like consider this pattern, and in this feature we have to design a transition table. Let's understand how this transition table is being designed. Suppose we are interested from 0, right? So delta 0 pattern is given 0. When we are at 0 state a, its meaning is that sigma p0 a, right? So this is delta p0 is epsilon, right? p0 is epsilon. There is no pattern up to p0. So this is epsilon into a. So this is sigma a, right? So sigma a, length of longest suffix of this, which is also prefix of pattern. So it has 2 suffixes, right? This guy has 2 suffixes, this epsilon and a. So epsilon of course is always matching with prefix of the pattern, but a is also matching with prefix of the pattern. And what is its length? Its length is 1. So that means delta 0 comma a is 1. This is the answer, right? Yes. So now we are interested in delta 0 comma b. Let's understand what is answer of delta 0 comma b. p0 b, right? So now sigma b, it has 2 suffixes epsilon and b. This has 2 suffixes epsilon and b. Epsilon is always there and b is not a prefix of the given pattern. So its length only suffix which is matching is epsilon, so this becomes 0. Here, this becomes 0. So same thing if we are talking about delta 0 comma c, this is sigma p0 c. Same, that means p0 is epsilon into c. So sigma c, and c is not prefix of this pattern. So definitely its answer is 0. Very correct. So this is how it is being done. Okay. Yes. So now consider transition from state number 1. So now delta 1 comma a, its meaning is that sigma p1a, right? So sigma p1a means sigma p1 is a, right? So this is a and a. It's very simple. So what are the suffixes of a and a? This has two suffixes, three suffixes, epsilon and aa. Which one is the longest suffix which is also prefix of p? Of course, a is the longest suffix which is also prefix of p, right? So its length is 1. So this is why it is coming as 1. Okay. So now if we are talking about next one, like delta p1, delta, let's say delta 1 comma b, 1 comma b. So this will be sigma p1b. Clear? So now sigma p1 is a and b, and we can see that ab is matching with this prefix, right? So its length is 2. So it's simple. Same thing p1 1c. So if we are talking about delta 1c, sigma p1c, and now p1 is ac. AC has two suffixes, C and A. None of them C. It has two suffixes, C and AC and epsilon. Of course, only epsilon is matching. So its value is 0. Yes. Okay. So let's talk about 2 and A. So delta 2 comma A means sigma P2A, right? So sigma P2, now P2A, right? So P2 is AB, P2 is AB, and then A, add A. So we can see that it has three suffixes, but ABA is matching with this prefix ABA. Its length is 3. Same as delta 2 comma B. If you see here P2B, so sigma P2 is ABB. Its suffixes are B, and then BB, and then ABB and epsilon. These are the suffixes. Look at them. In the prefix of P, B is not matching. BB is also not prefix of pattern, right? And ABB is also not prefix of the pattern. Only epsilon is prefix of the pattern. So that's why this is 0. This is 0. This is 0. Same thing 2AC, you can also see delta 2 comma C, sigma P2, P2 is ABC, and its suffixes are epsilon, then C, BC and ABC. None of them are matching, especially this, so its length is 0. So this is 0. So let's consider this transition on 3. Let's consider transition on 3. Transition on 3, delta 3 comma a. You have to consider all the transitions, especially a, b, c on on the alphabet. So this is sigma p3. P3 is now a, b, a, right? And then append this guy over here, right? P3 is a, b, a. So now its suffixes are a, and then b double a, and then a, b, a. It has 4 suffixes, and of course epsilon is by default, right? So look at them. A is prefix, its length is 1, AA is not there, B double A is also not there, AB, AA is not there, epsilon is there. So longest suffix which is prefix of P is A, whose length is 1. So this is why it is coming as 1, right? So similarly, if we are talking about delta 3 comma B, delta 3B, transition on 3. So sigma 3 A, B, A, and then B. It has suffixes, 5 suffixes. B not matching, AB is matching. Okay, like 4, 3, yes, 3B, yes, it has 4 suffixes. B, yes, suffixes B, and then AB, BAB, and ABAB, right? So this B is not prefix. AB, yes, it's matching with prefix of P, its length is 2, and then BAB not matching, this is also not matching, right? And then ABAB is matching, its length is 4. So we are interested in the longest suffix, its value is 4. Same as 3 comma C, delta 3 comma C, P3, sigma P3, AB, A, and then C. So we can see that this is actually C not matching with the prefix, AC is also not there. So it only suffix which is matching is epsilon, so whose length is 0, right? Okay, so similarly, okay, okay, so let's randomly calculate this 7A. So delta 7A, right? So P sigma P7A, sigma P7 is complete, ABA, BA, and CA, and then attach with A, right? So only one prefix, one suffix A, which is found as prefix of the pattern. So its length is 1. So we can get that this is 1. Similarly, all other transition can be defined. So okay. So how this, having done with this finite automata, now question is that how we are going to match pattern inside the particular text. This is the transition table, or from this transition table we can design a particular finite automata, right? Okay. So now this is pattern, and this is given as text. So this is your text. We can see that this pattern is occurring in ABA, BA, and CA, right? So we can start from 0, then A is 1, then 1 and B is 2, then 2 and A is 3, then 3b is 4, 4a is 5, 5b is again going to get 4. That is how it is using the previous biology, right? 4a again 5, then 5c is 6, and 6a is 7. Now 7 and b, this is going to match. Had it been supposed, again you are going to get this one, so no need to go to the previous point. It will match completely, right? So this is how it is utilizing the previous value. Another example, suppose we have pattern ABCAB, same thing over here. This is suffix which is also prefix of the pattern. AB is matching over here. Look at here. So in the same way we can design this transition table. It's the same thing. There is no big difference, right? And this same transition table we can define. We can check here, like see any transition table. Let's say randomly, like delta 3 comma A is sigma P3, P3 is ABCA, right? So its value is 4 because entire pattern is matching with the prefix. So we can design the finite automata and we can see that ABCAB by this transition table. So no need to design this finite automata. We can find out pattern inside the text by using the transition table itself. Thank you.